Inviting me to talk in this meeting, and I have to apologize that I had to cancel my in-person participation last minute, but I know that you have quite a few people from the University of Illinois in the room, so I will point them out to you by name at least as appropriate. And what I want to talk about today is application of numerical relativity to probe physics beyond the standard model, and in particular thinking about how can we probe for theories of gravity that go beyond Einstein's general relativity. Now, these may be motivated from ideas of how can we combine gravity and quantum physics. I'm not going to do quantum gravity, I promise you that, but any model of quantum gravity typically predicts modifications to Einstein's general relativity, and we may be able to search or understand signatures thereof if we look at black holes where gravity is the strongest. So this is kind of the motivation of bringing the tool of numerical relativity beyond Einstein. Now, if we want to probe for either properties of general relativity or extensions thereof, we typically want to understand very well how, first of all, compact objects and black holes form, which is actually my second item here on the list, what their properties are and if they are stable. And if they are stable, then we can think about, well, what happens if we put those two compact objects in a binary and they may, in spiral merge and ring down and emit gravitational waves in this process. If that happens, then we can try to use gravitational wave observations to probe for signatures of new physics. Now, if we want to do that, we better also know very well how such a gravitational waveform looks like theoretically. And to do that, we need both a consistent modeling of the in-spiral merger and ring-down signal in general relativity, in the large parameter space that we have in general relativity, and also in extensions thereof. And this is really crucial to build waveform templates to then characterize our signal. So if I look at this example here, which is actually an image from Hector Okada da Silva for an late in spiral merger and ring down. And what you see here in highlighted colors are a few ways how a waveform may differ in extensions of the standard model. So typically what we find is that there's either a change in amplitude or in frequency that we can then model. And as I said, for today, I want to focus on the merger part. Okay, so the next slide I think is going to be a little bit busy. So I will break it down bit by bit, just to give you an idea of where we stand in applying numerical relativity to modifications of general relativity. And to do that, I like to use Lovelock's theorem as a guideline. And he tells us that in 4 space-time dimensions, the only divergence-free symmetric rank 2 tensor constructed only from the metric and its derivatives up to second order and preserving diffeomorphism invariance is the Einstein tensor plus a cosmological constant. So if we want to go beyond that, we would typically break one of these 4 pillars that I've highlighted here in blue. I'm not going to talk about going beyond 4 space-time dimensions, although I know that this actually has been a very interesting and active field for quite a while. I know, Eric, you have been working on this as well. I've done this in my PhD some 10 years ago. But now I really want to focus on the other 3, where we say we can either have extra fields, or we can look at theories that have more than just second derivatives of the metric, or there's some early work on breaking diffeomorphism invariance. And again, we don't have to go through everything in detail, but just to give you a flavor of what's been going on in this field. And you see there has been some early work about 10, 15 years ago, mostly on scalar tensor series, which is the most straightforward modification to general relativity. And then there has really been, I think, a lot of work over the last 4 or 5 years, which you can see here. I'm happy to share the slides if anyone's interested in the references. And I also want to highlight that I'm not going to talk about everything that's on this slide. So this is really just to give you an idea of what's been going on in the field. And I want to focus mostly on models with higher derivative corrections. I think I would touch upon effective field theory of gravity, and I will show you in an action how all of this looks like. And I will touch a little bit upon work where we just look at very light scalar fields around black holes. So this is not necessarily going beyond Einstein, but it's going beyond our standard model in particle physics. So this is where we stand at the moment. So, as I said, for today, I do want to focus on a subset of this body of work, looking at higher curvature corrections that become relevant in the strong curvature regime. Now, where might these come from? And there's two ways of thinking about it. So you can either say, well, I want to modify Einstein and see what happens in the high curvature regime. And let me think about taking a series expansion in curvature. And this is one of the things that we will look at. So you can take Einstein with your Einstein-Hilbert term, so just the Ricci scalar, as your lowest order term in a series expansion in higher curvature, and add terms that are curvature squared. And this is something that we would probably call a bottom-up approach, building from the bottom up to think about what could be a complete theory. You could also take the reverse and say, oh, let's take a class of models that have been proposed as candidates for quantum gravity, such as string theory, and let's take that and now take a low energy limit of this, which gives you supergravity in high dimensions, and then do dimensional reductions down to 4 dimensions. And people have actually worked this out explicitly, and you end up with a very similar action. And I'm just actually writing down the Lagrangian here. So what do we have here? We get our beloved Einstein-Hilbert term, just the Ricci scalar. Then we can add a curvature invariant. This curly G here is a specific combination of the Riemann tensor squared, Ricci tensor squared, and Ricci scalar squared that gives you second order derivatives of the metric to a higher power. And this curvature invariant is now coupled to a scalar field that I call phi. And we also have the kinetic term for the scalar field here. I didn't write its potential, but we could also add a potential for the scalar field. So that's one correction that's quadratic in curvature. Now, the other term that you would get from this top-down approach is called dynamic Schoen-Simons term. So you get a Riemann times dual Riemann, or actually this reduces to Ricci times dual Ricci here. So this is called the Pontryagin density. And again, gives you a curvature squared correction, now coupled to a field that I call theta, which is an axion-like particle, and we have its kinetic term here. So these are the two models that I may be focusing on the most, and I will try to be consistent with the color coding here. And people also started thinking about what's called effective field theory of gravity, where you say, where you really take this idea of a series expansion in curvature seriously and say, okay, the first order term is my Ricci scalar, and then I add terms that go like Riemann squared, Riemann to the cubed, and so on and so forth. Yeah, and there has been very nice work, for example, by Aaron Held and Ramiro Cayuso in this regard. So this is what we want to focus on today. And one of the first questions that we may want to ask before even sitting down and implementing a code is, well, if I take this, if I derive my equations of motion, are they actually mathematically a well-posed initial value problem? Because that's something that is necessary for numerical stability. And the answer is, well, it's actually not that simple, because this green term here gives us, well, I said second order derivatives of the metric, but to a higher power, so second derivative squared. So these are nonlinear terms. This dynamical Schoen-Simons term here gives you third derivatives of the metric. And again, it's actually not obvious that this can be made well post. And about 10 years ago, we showed that it's likely that you cannot make it well post. So how do we deal with these kind of theories? And luckily, we now actually have different ways of dealing with these type of equations. So I'm just writing it here again. So we can have higher time derivatives. We can have equations because of these non-linearities end up having some kind of mixed hyperbolic elliptic character, different from Einstein's equations. I know in Einstein's equations, we can do the space-time decomposition of the equations and neatly, divide out a sector that is a set of elliptic equations and a set of hyperbolic equations. So these are our constraints and our evolution equations. So what I mean by mixed hyperbolic and elliptic is different. So here I'm thinking about one differential equation that in some regions of our space can be elliptic and in other regions of our space-time could be hyperbolic. Yeah, so that's a very different beast than what we are familiar with. Now, as I said, we still need to think about how can we write these equations of motion as something that's causal and well posed, because we need that for numerical stability. And there are three approaches now that have emerged. And the first one is probably the most straightforward that you can think about. I call this order by order expansion or order by order approach, where you take your metric and your additional fields and you expand them around some background field and you take as expansion parameter your coupling parameter. So in the previous slide, that was this alpha GB or this alpha CS. What happens then, if you work this through, is that at each order n in this expansion, you get the just Einstein tensor computed from your background, which is general relativity, acting on that nth order of the metric, and you get an effective energy momentum tensor that depends only on the lower orders. So anything that comes from the lower order just enters as a source term. And likewise for these extra fields that your D'Alembert computed from the general relativity background metric acts on the nth order. And then we have a source term that depends only on the lower orders. So that's something that's very easy to implement, right? Because in the end of the day, you're dealing with just a wave operator acting on a field with some source terms. So we can control very nicely what's going on. And this is particularly useful if you want to just think about, say, stationary objects. So if you want to compute what your black hole or your compact object is and whether it's stable, that's something you can, where this approach can be very nice. Or if you say, I want to just see the features of the scalar field or this additional field in this background, then this is also a suitable approach. However, to compute the gravitational radiation, so if we want to go to a higher order in the metric to actually see what the modification is, then you end up having secular effects. So things that are not necessarily physical and just an artifact of this approach. And you can actually see that. I will show you one of those examples towards the end, where you find a strong dependence on some of the simulation parameters just because of these secular effects. So there's some ideas on how one might regularize this by Leo Stein and his student, but I think the paper is for a toy model, so I haven't yet seen it for the full problem, which I think is notoriously hard to do. Okay, so this is an order by order approach, and this is something that because of this overall feature, something that's easy to implement and easy to do, and gives you some insight into the numerics. Good. So the next approach is actually inspired by relativistic hydrodynamics. And that goes back to a paper by Louis Lehner and collaborators and students, where they say, okay, in relativistic hydrodynamics, what do we do if we need to deal with our higher derivative equations? It turns out that Navier-Stokes equations themselves, for example, are also not well posed. And what you do instead is to introduce an auxiliary field that takes care of some of the higher derivatives or of the nonlinearities. And then you introduce a somewhat ad hoc equation that drives this extra field to the solution that it should be. And this is something that's regularly done in, as I said, relativistic hydrodynamics, following Israel Stewart. Now, to see this in a toy model, let's just look at an equation like this. So we have our wave operator acting on a field. And on the right-hand side, we have, say, force derivatives of this field. And this toy model actually is something that you would get if you would derive a toy model for some of these higher derivative theories. Well, if you look at this model itself, you find that they are superluminal modes. If you just do a mode expansion of a mode analysis for this equation, you find they're superluminal modes, so it's acausal. How could we fix it? Well, we could introduce a new field called pi, which is just a second spatial derivative of the original field, and rewrite our equation as wave equation for phi, and now with a second derivative of this new field. And we would introduce a wave equation for pi, which now, if you work this out, goes like, well, the initial definition, second derivative of the scalar field, and we add these ad hoc terms here, where tau is a time parameter that basically gives you the time scale on which pi is driven towards its actual solution. And this, if you now do a mode analysis, is something where you have causal evolution. And people have actually implemented this, and I will give you a more concrete example later on. And then the last approach that people came up with afterwards is to think about modifying the gauge conditions. And the original idea by Aaron Kovacs and Javier Real was to take the generalized harmonic gauge, which is used with a generalized harmonic formulation, and modify this. And the idea here, there we go. So, and here the idea is that you introduce a set of two auxiliary metrics, and your gauge degrees of freedom propagate along the light cone of these auxiliary metrics, such that everything that, all the physical degrees of freedom, again, are causal with respect to these metrics. And by now, we actually have equivalent formulations thereof using Z4 formulation. And I will show you examples of these as well. Okay, so these are the three main approaches that we have, and I will come back to point those out as we go along. Now, with all of the theory now set up, let's think about compact objects and binaries of compact objects. And the first thing that we want to think about is what does a black hole do if we add extra fields, or if we consider these higher curvature corrections. And here we see three equations. Sorry, a bit busy, but let's start with the one here on the left, where I'm now taking just this axion-like particle. So theta is, think of it as a scalar field, and add a mass term to it. So this mu is just the mass energy parameter of this field. And people have shown that you can grow condensate of this field around a black hole, either through a process called superradiance or through accretion, when this mass parameter times the mass of the black hole are of order 1. So this, what does it mean? Well, this mu, you can associate wavelengths to this mu. So if the Compton wavelengths associated to this mass parameter is comparable to the size of the black hole, then you can actually form long-lived scalar clouds around the black holes. So it's not exactly a hairy black hole, but it's sufficiently long-lived to think of it as a hairy, in quotation mark, black hole. And then the other two types that I want to think about are for these quadratic, so for these corrections of general relativity that are quadratic in curvature. So remember, I told you this curly G here is essentially a Riemann squared type correction. And here we have what's called the Pontryagin density. So Riemann times the dual Riemann. And in both cases here, you see that we have a wave equation for our field with this as a source term. So even if we were to start with a zero scalar field, then having the space-time curvature here, even for a single non-rotating black hole, will source the scalar field, and you will end up with a black hole that has a scalar charge. And here on the right-hand side, very similar. This Pontryagin density is non-zero if your black hole is rotating, and again, will source this theta field, even if you start your evolution with a zero field. Okay. Okay, so one item I have here is that black holes have scalar charge, and by charge, I really mean the leading order contribution in my scalar field. And neutron stars do not have this term. So they do have a scalar field around them, but with a higher order in 1/r. Okay, so one question one might ask now is, how do we actually form such a black hole with a scalar charge from stellar collapse, right? If I just tell you a star does not have this charge and a black hole has, what causes this charge? And this is something that we looked at with Abhishek Hegade, Elias Moos, Josh Noren, and Nico Yunus a couple of years ago, where we simulated stellar collapse in quadratic gravity. I have to say we were working in a decoupling approximation. What I mean by that is that we have our background being described by general relativity. So we were just evolving a TOV star in the background that was collapsing into a black hole. And we evolved the scalar fields phi and theta sourced by this background. And the example that I'm showing you here on the left is a space-time diagram for the scalar field phi, so for this green equation here. And the color coding is the amplitude of the scalar field. Yeah, so what you see here is we start with our TOV star in the background. And as I said, there is some much lower order scalar configuration around it. It's just not the leading order charge term, so the charge over R. This is absent in the star. So here the amplitude of the scalar field is very low. And as our star collapses, we in the background, we track the formation of the black hole. We track in the simulation the formation of the apparent horizon here in red. And we also computed backwards, computing the event horizon, which is here indicated in blue. And what we could see is that the formation of the event horizon triggered the excitation of the scalar charge. So here in the amplitude, we only see the scalar charge being present. Later on, looking at the scalar field flux, we see that it really starts growing as soon as the event horizon has been formed. So long story short, if I have a single black hole, so if I have stellar collapse, then the scalar field in these quadratic gravity series is triggered. Sorry, not the field, the scalar charge is triggered when the event horizon forms. Okay, good. So now I also want to advertise some work that we did with Chloe Richards, one of my students here at the University of Illinois, and our former postdoc, Alexandro Dima, where we evolved one of these scalar fields, the theta field, now sourced by the Pontryagin density, and adding this mass term. So basically, the questions that we were thinking about here is the following. So if I get rid of this red term here, and I just have a massive scalar field where I told you I can form a cloud around a black hole, how is that affected by adding this higher curvature invariant, and vice versa? If I have this modified gravity theory and there's a process that gives rise to a mass term, how would that affect our hair? Before I show you the simulation plots that are very busy, let me actually just talk about the qualitatively the features that we would expect for each of these cases. So again, let's get rid of the Pontryagin density here and look just as at the mass term, which is in blue. this would give rise to a scalar field cloud, as indicated here, which is dominated by an L equal M equal 1 dipole. So this is what we are indicating here. And it's this field, this cloud, is oscillating with a frequency that's determined by this mass parameter mu. Okay, so if we now get rid of this mass parameter and just look at the feature due to the Pontryagin density, then this one gives rise to a hair, which is indicated here in red. So this is an axis symmetric configuration, L equal 1 dipole, M equals 0. And this truly is a hair in the mathematical sense. Now, as I said, the question is, if we switch both on, how will this affect our field and our field configuration? And to see this, let's have a look at our snapshots from our simulations here. So I know this is very busy. So let me talk you through this. On the left, I'm showing you the equatorial plane, so y versus x. On the left-hand side, it's a simulation in GR with just a mass term, so getting rid of this red term here. And on the right-hand side, this is switched on. And the question here was, how does this higher curvature coupling affect our massive scalar field? And well, from the snapshot, you don't see any difference. Actually, looking at the data more precisely, you don't see any difference. So in the end of the day, this higher curvature correction does not affect the massive scalar field cloud, which might be expected given that this affects the axisymmetric mode that's aligned with a black hole spin. Now, the picture is a little bit different when we look at the plane that's perpendicular to the equatorial plane, so aligned with a spin. So that's the ZX plane. The spin of the black hole is indicated here. And again, on the left-hand side, it's a simulation in general relativity, just with a massive scalar field. And on the right, we have our correction due to the Pontryagin density, where we see this dipole structure emerging due to the Pontryagin density. And then if we were to zoom out, we actually see that now instead of just having the dipole here, this field starts oscillating, and again, with a frequency determined by this mass parameter. So this is what we have for single black holes. So what you should take away from this part is that if we modify general relativity, in particular, if we add these higher curvature terms, then we end up with black holes that can have a scalar charge. And now you can think about what happens if you put those in a binary. And actually, one shout out to Nora, who I think is in the room, who's working on a very similar project, but now having here the Gauss-Bonnet invariant. So if you're interested to hear more about it, just go talk to Nora. Okay, so now let's think about the binary. And again, let's start bit by bit. And I know many of you may have seen this animation already, where we took two black holes in this scalar Gauss-Bonnet gravity, where our black holes have scalar hair. And what I will show you in the animation is the evolution of the scalar field driven by two black holes described by general relativity. Okay, each of these black holes has a scalar charge, and two black holes actually is a relatively simple setup. So I have black holes that are not spinning, that have a mass ratio of 1 to 2. And what you already see here is the scalar charge associated to each of the black holes. Since the scalar charge is determined by the curvature, the larger charge is actually around the smaller mass black hole, which has a higher curvature here. So if I let this evolve, then what you can see is that as our two scalar charges are orbiting, they generate scalar dipole radiation. Right, so this is what you can start seeing here. And so as I said, you see the scalar dipole radiation being emitted here. And now you can ask, well, what does this actually do to my binary black hole if I were to include the back reaction of the scalar field onto the metric. And what will happen is that now our scalar field is carrying away energy, is radiating energy away. So it would accelerate the in spiral. And because our gravitational wave frequency is tied to the orbital frequency, that means our gravitational wave signal would also have a faster frequency evolution or phase shift compared to just the vacuum GR phase. And that's something that we early on had computed with Banafshir, Shirali, Lutanya, Hindra, Samaya, Nasanka, Nestor, Ortiz back in 2020, 2021 in a post-Newtonian fashion, where Banafshir derived the leading order corrections to the post-Newtonian waveform, so describing the in spiral due to this Gauss-Bonnet correction. Now, what you're seeing here in this plot in the top panel is the gravitational wave strain as a function of time, and in the bottom panel, the frequency evolution as a function of time. The black curve here corresponds to our signal in general relativity for a black hole with a binary with a mass ratio of 1 to 2. And for specificity, we set the total mass of the binary to be 15 solar masses. So something that would be in the LIGO band. And for comparison, we have here in blue the waveform computed in the scalar Gauss-Bonnet gravity. So basically, the analogous setup to what we've seen here on the left. And what you can see now in the gravitational waveform, where we computed the full correction to the waveform, is indeed this gravitational wave phase shift compared to the general relativistic counterpart. Now, I should point out that all of this has been done so the left-hand side simulation has been done in this decoupling approximation or order-by-order expansion, where I said, well, it's nice to look at single black holes and to just get the dynamics of the scalar field, but it really is not a very good approach to compute the back reaction onto the metric. So this is work that has been done in the following, and I actually want to, oh no, I didn't want, let me actually just go there and skip this part here, because I think people have seen this. So let me advertise some work by Max Corman, Justin Ripley, and Will East, where they again looked at this scalar Gauss-Bonnet gravity theory. As a reminder, what you have is your Einstein-Hilbert term, dynamical scalar field, so this is just a kinetic term for the scalar field, and then a coupling between the scalar field and the Gauss-Bonnet invariant. And here they used the modified generalized harmonic gauge. Or in other words, they actually solve this theory in full using a new gauge condition. And one of the examples that I wanted to show you here on the left, where they could actually simulate the full coalescence, is for a black hole binary, no spin, equal mass. And I think their coupling parameter zeta here is related to our alpha GB, possibly with a factor of 2 in between those. And what you see here in the top panel is the scalar dipole radiation. Sorry, not quadrupole, so the L equal M equal 2 mode for the scalar field, the L equal M equal 4 mode for the scalar field, all rescaled by the extraction radius. And then here in the bottom panel, the gravitational radiation computed using the Newman-Penrose scalar and the L equal M equal 2 mode thereof as a function of time. And yeah, so what you can see here are several things. So this is our scalar dipole emission, quadrupole emission, I'm sorry, compared to the post-Newtonian calculation. And then the important bit is that actually, yes, they could go through the entire simulation, modeling the merger of two black holes in full in this theory, and giving us an understanding on what the gravitational wave signal would look like. Surprisingly simple, probably. I think we all expected a little bit more going on here, but again, we couldn't know that unless we went about looking for it. So this was really nice work by Max. And one of the issues that she reported in the original paper is that for some cases, so for example, even just going to a mass ratio of 1 to 2, they saw a breakdown of this new gauge conditions close to merger. I think by now they fixed this, and there's actually a body of follow-up work both by Max and also by people like Katie Clough and Daniela Doneva. And I think you saw one of Katie's talks earlier this morning. Okay, so that's the full approach.
10 minutes.
Yep, I know. Good. So I did want to advertise actually a little bit more work, not only by my group, but also by others. And this is a paper by Libert Salon, Katie Clough and Pau Figueras, where they also looked at black hole simulations in scalar Gauss-Bonnet gravity. This is a green term here, but they also included all the scalar field terms that would come at a similar derivative order. So this is what they have here. And the important bit is that they are using now a ZZ4 formulation with a modified puncture gauge that has been inspired by this modified generalized harmonic gauge. But since so I think if you're an Einstein Toolkit user, you are probably much more familiar with using BSSN or Z4, a variant of Z4. And now the good news is this is actually also available. And here what they're showing are simulations of binary black hole with equal mass, initial separation of 11m. And what you have here is, again, the leading order quadrupole mode of the gravitational wave signal. Here it's the strain as a function of time. And the different curves here correspond to different choices for the coupling. And I'm sorry, every group uses a different coupling parameter. So this lambda GB now again is related to what I called alpha GB earlier, but this is the coupling parameter to the Gauss-Bonnet invariant, and G2 is a coupling parameter to the scalar field. And in this plot here in blue is a GR waveform, which you can see here underneath the orange one. And then if you have a small coupling to the higher curvature invariant, these are actually almost lying on top of each other. I think here's an inset, a zoom in of this case. But if you increase the coupling constants, then you do indeed see this dephasing that I mentioned earlier, so a faster in spiral due to this extra emission of scalar radiation. And I believe this implementation is now also public in their open source code GR4S, which is working with GR Jumbo. Yes, so this is a reference to the paper that they have. Good. So let me see. So the last approximation or approach that I wanted to tell you about is this fixing of equations inspired by Israel Stewart. And this is something that Ramiro Cayuso has been spearheading for an effective field theory of gravity, where you have your Einstein-Hilbert term and then a Riemann to the force. So Riemann squared, Riemann to the force kind of correction, where you also get modifications to your black hole solutions and potentially to your gravitational wave signal. And here they used a combination of first reducing the order of the equations and then fixing those equations a la Israel Stewart, as I described before. And again, the proof of principle simulations that they did were binaries with an equal mass, separation of 12m. And here on the right-hand side, you see an example of the simulations plotting the quadrupole gravitational wave mode, again, the strain as a function of time. And in the bottom panel, the phase of each of these evolutions as a function of time. Here, the blue curve, so the middle one corresponds to general relativity, and depending on their coupling strengths, which now is called epsilon, I apologize, this can either lead to an earlier merger or to a later delayed merger. Okay, so one of the questions that you might ask now is, well, if we have all of these different approaches, and I already hinted at, some of these approaches may depend more on parameters than others. How robust are these different approaches? And let me just flash the slide that I had earlier. I'm not going to go through it again, but just to remind everyone of what I was saying before. So we have this order by order expansion. We have this fixing a la Hydro or a la Israel Stewart, and we have evolutions of the full equations using modified gauge conditions. And this question of how robust are these approaches is something that Max Corman answered very recently, actually, just a couple of weeks ago, where she performed simulations of binary black holes in scalar Gauss-Bonnet gravity using all three approaches. And what she did was to simulate binary black hole with parameters similar to GW150914, so the first binary black hole that merger that we've ever detected. And the first plot that I'm showing you here is comparing the full evolution with this order by order expansion. So there are a lot of, and again, what I'm plotting here is a quadrupole gravitational wave strain as a function of time, where we have in black is just general relativity. Then the green and the pinkish curve are the full evolution for two different parameters. And you can see those here, I think, most easily in the inset. And then she compares that to this order by order reduction in the bluish curves here, the dashed lines. And what you see is that these dashed lines seem to give a much, much higher amplitude and phase shift than you would get from the full solution. And this, I think, is in part due to these secular effects that I mentioned earlier that are actually not physical and just an artifact of the approach. Now, she did a similar comparison for the waveforms in scalar Gauss-Bonnet gravity here in green and blue. So these are these two lines here. And then changing the time scales for this fixing approach. And you can see that depending on this time scale, which is really just a parameter in your simulation, the merger can appear to happen earlier or similar to what you would get from the full solution. So as an upshot is that what we can see here explicitly is that there's a strong dependence in numerical parameters, both in the order by order expansion and this fixing approach, and that the most accurate approach, if it's available, is really using this modified gauge condition that gives us the most accurate evolutions. Now, I know I have about 2 minutes left, so I wanted to skip this and shout out to Cheng Ching to tell you about his work. But one of the things that you might be interested in is, if I do want to study physics beyond the standard model, can I actually do some of the simulations with the Einstein toolkit? And the answer is yes. We do have a lot of the work that I talked about, especially from my group, implemented in the Einstein toolkit, in Canuda, sorry. And Canuda is an open source numerical relativity code for fundamental physics. It's based off the Einstein toolkit. Some of the arrangements are in the Einstein toolkit, some are not. So if you want to look at our code, use our code, here's our Git repository. And the pictures that you're seeing here are just some examples of work that we've been doing. You've seen some of those images before. I also want to highlight that it's not just our group. So for example, this is work done in Lisbon and Rome, work done in Valencia, where they used our code for their simulations. Now, what do we have in Canuda? And this will be my last slide before the summary. So what do we have is a set of arrangements that actually can do just space-time evolution in general relativity and wave extraction using Newman-Penrose scalars. So this has been already available. I know people have partially used this or compared code to it. And one of the things that Deborah Ferguson, who's our postdoc here in Illinois, is doing is to now implement output so that we can use the Cauchy characteristic evolution from Spectre. And I think she will tell you more about this tomorrow. So talk to her if you want to learn more about this. We are also moving part of our code to be compatible with Carpet X, and that's something that you want to talk to Chengqing, Deborah, and Nora about who are in the room. We have options to add additional scalar or vector fields to general relativity, and for the scalar fields, talk to Chengqing. And all of these three here with an asterisk are already part of the official Einstein toolkit. And then the other two for modified gravity, so in particular Gauss-Bonnet and dynamic Simons in this decoupling approximation are also available. And for Gauss-Bonnet, talk to Nora because she actually has been extending our current code and is in the room. Okay, so with that, let me not go over this and just give you a summary that I've shown you quite a few examples on proof of principle simulations for compact binaries in a class of extensions of general relativity that typically give extra scalar radiation and therefore lead to dephasing in the gravitational wave signal. If you're interested in doing some of those simulations, there are several open source codes. Canuda is the one that is compatible with the Einstein toolkit done by our group. And there's also the GeoJumbo version thereof. And I think I will leave you with that so that you actually have time to ask questions. And thank you for your attention.
So we have quite a bit of time for questions, about 14 minutes or so. You can hear me actually.
Yeah.
Can you hear me?
So I can hear one person speaking.
That's me probably. Okay. I can't hear myself right now. Okay. We actually have one more speaker before the lunchtime comes about. So Anush, if you are able to set up your laptop, go to Zoom, log in, then we can save a bit of time. With that, any questions from the room for Helvi? Zach is first.
Thanks, Helvi, for the very nice talk. I'm very curious about how you intend to address the concern about eccentricity reduction in initial data, given that we don't have necessarily post-Newtonian theories for every alternative theory of gravity.
Yeah, so this is a really good question. I should say that in our cases where we are only a very scalar field sourced by a binary in GR, we know what to do. Okay, so one example where we did do this very carefully that I haven't shown you here is where we coupled just a massive scalar field to Einstein's equations, and this is something that Chengqing actually did very carefully, starting from the closest post-Newtonian parameters where they are available, or starting with the parameters that we have for the binary in vacuum, and then do it iteratively. Because you can still estimate the eccentricities, say, from your gravitational waveform. Does that make sense?
Yeah, I mean, I guess the idea is it's not necessarily going to be as efficient as
it's not. No, it's not as efficient. Absolutely not. So it's it actually took a lot of time, and it's not very efficient. But it's also true that there are cases where we don't have post-Newtonian estimate. So we have to start with whatever is closest to this, and it's not efficient. Now for these simulations in modified gravity, so the ones that I've shown you, I don't think they actually cared about eccentricity reduction. So they just started with a set of parameters, and at least in some cases, I know that they haven't been thinking about it very carefully because it really was a first proof of principle. We can do these simulations in the first place. And now the next step, especially if we want to use those waveforms for data analysis, we need to think about eccentricity reduction. So this is a very, very good point, but I don't think this has really been done rigorously yet.
And there's one question online, Helvi, in chat.
Okay, there are some jargon in there that I don't know. Okay. Okay, so I see. So, okay, let me start with the second one, because then the first one I think is something to go back to the paper. So this one of the questions is, how do you compute the Weil scalar in the context of modified gravity in general? And here, I think what people have been using is the fact that the additional scalar fields that you get, or the corrections due to these higher curvature terms, fall off at a high power 1/r. So I think what they've been doing is compute psi4, so the Weil scalar still, using our standard approach, because far away the corrections from our higher curvature terms are negligible, so that these high curvature terms really only affect the dynamics of our binary. Whereas then perturbations far away are basically general relativity plus a very small correction. And there are papers showing that in perturbation theory. So this is, I think, what has been happening there. And then the other question is, how can I adapt the usage of the tetrad, as we may see in parallel gravity, in numerical relativity? So that's something that I actually have not done. So I honestly say I don't know the answer to that question, but it would be interesting to think about. And I think there are there may be a few works. So the only place where we are using a tetrad is when we compute the Weil scalars. But this is really it's done during the simulation, but using the data that we've computed on each time slice. So I don't know if anyone else in the room has an answer to this.
No one is raising their hand.
Okay. So yes. And then, yeah, and then for the first question, so the Dyer approach is a post-Newtonian approach in post-Newtonian calculations to the near zone, to apply that for scalar Gauss-Bonnet gravity. And I think for the details, I would refer you to the paper that we have with Banafsheh Shirali-Lu, because that's where she wrote this out in detail, how we can do that. Yeah, as a quick answer, because I know that we have another talk coming in a moment.
We have one more question. Drew?
Yeah, you may have mentioned this in any episode, but can you also get degeneracies with possible GR, like different mass and spins?
Sorry, can you repeat your question or come a bit closer to the microphone?
So if you do like a beyond GR simulation with some mass and spin, can you get degeneracy with like a classical simulation of a different mass and spin?
Yeah. Well, so I'm saying yes, because I do see very similar features. We actually haven't tested that rigorously. Again, it's one of those things that we need to check very carefully. And I think we are really at the status that, okay, now we do have the first simulations and we can actually start addressing those questions, and it needs to be done. But I think my top of the head answer is that yes, there may be degeneracies, and I don't know if we can break them. Does that make sense?
Yeah, thank you.
Okay, very good. Yeah, and the other thing, looking at this last item here, because I didn't tell you about environmental effects. So this is really work that we've been doing with Ching, who is in the room, where we modeled one environmental effect with a scalar field. And what we are seeing there is also shift in the gravitational wave phase, and I'm in the gravitational wave phase due to the presence of this long-lived scalar field. And it looks very similar. We haven't done the actual data analysis, but just seeing this behavior, I would be very, very cautious in interpretation of seeing anything that deviates from vacuum GR in the parameter space that we've modeled. Yeah, so it's something that I think we all need to be very careful about.
Thank you. Seems that's all the questions we have. So let's thank Helvi once more for a very interesting talk.
Okay, thank you. And let me stop sharing.